Hi, I'm Matt, and in this video we are going to go over the history of atomic structure and the major developments that led atomic science to what it is today. So we're going to go from past to present when it comes to the atomic models, starting with Democritus, then Dalton, Thompson, Rutherford, Bohr, and then the current wave mechanical model. Now, to start with the history of atomic models, we have to go all the way back to ancient Greece. So in approximately 400 BC, Democritus proposed the idea of atoms, with an atom being the smallest unit of matter that can't be broken apart any further. Now, Democritus didn't really use science, but instead it used a thought experiment, that if you were to keep breaking something, eventually you would get down to pieces that were so small you couldn't break them apart anymore. Democritus called these things that you can't break up any further atoms, because atomos in Greek means indivisible. Next, we're going to jump to John Dalton in 1803. He proposed that an atom is a small, indestructible sphere, and that there are different elements, and they are made up of different types of atoms. To prove this, he used the law of definite proportions. This stated that compounds are made up of different elements that bond in fixed ratios. For example, water always bonds in H2O. If it bonds as H2O2, we have a different species with different properties. The next major development came in 1897 with J.J. Thompson. He concluded that atoms contain both positively charged particles and negatively charged particles he called electrons. He also developed the plum pudding model, where there are electrons represented by my red circles in the diagram in a positively charged cloud, which is that whole blue area. To prove this model, he used a cathode ray, which is basically a tube with a beam of light in it. And he realized that he could deflect this ray away from the negative end of the terminal to a positive end if there was a magnetic field or an electrical field. Using this, he concluded that there has to be electrical charge or electrons in an atom. The next major development came in 1911 with Ernest Rutherford. He concluded three main things: that atoms are mostly empty space, atoms have a dense positive nucleus, and that electrons orbit outside of the nucleus. To prove this, he used the gold foil experiment. What he did is he accelerated or shot alpha particles at a piece of gold foil and observed that most of the alpha particles passed through since an atom's mostly empty space. However, a few hit that small dense nucleus and bounced back, proving that there is a small dense nucleus. Shortly thereafter, in 1913, Niels Bohr created a new model of the atom called the planetary model. There was still that small, dense, positively charged nucleus, but Bohr concluded that electrons travel in orbits around the nucleus, represented by those green circles, and he called his model the planetary model. To prove this, he used emitted light, that when an element is heated, it emits a certain colored light, or a series of different colored lights, which was known as its spectrum. And the specific wavelengths needed for the electron to move between the levels was called quanta. And he realized that every element has a unique emission spectrum, therefore the electrons must be in fixed orbits. The last model we are going to discuss is the wave mechanical model. This was not just one scientist, but was the combined work of many scientists, one such being Schrödinger. And they concluded that electrons do not actually travel in fixed orbits, like Bohr's planetary model shows, but instead travel in orbitals. Orbitals are just realms of probability. They're where the electron is most likely to be, but we can never exactly know where an electron is. They also concluded that electrons exhibit wave-particle duality. Electrons act as a wave and a particle at the same time, and just using one of them cannot correctly describe its properties. Lastly, here are 6 practice questions to test your knowledge of these models we went over. So question 1 is, which experiment led to the conclusion that most of an atom is empty space? Question 2, J.J. Thompson used cathode ray tubes to prove the existence of what particle? What was its charge? Question 3, which scientist used light emissions to prove the planetary model? Question 4, which scientist concluded that atoms were small indestructible spheres? And question 5, what is the term used for the most likely location of an electron? And then for question 6, I would like you to order the 6 models and scientists we talked about in this video. The answers to these questions will be provided for you on the next slide. The answers are as follows. The gold foil experiment proved that atoms were mostly empty space. J.J. Thompson discovered the electron, and an electron has a negative charge. It was Bohr who used emission spectrums to prove the planetary model. Dalton said that atoms were small indestructible spheres, and an orbital is the realm of probability for where an electron is most likely to be. And then from earliest to most recent, the scientists go as follows. Democritus, Dalton, Thompson, Rutherford, Bohr, and then the wave mechanical model. Now, one last closing note, just because a model isn't exactly what happens doesn't mean it's not useful. Often in chemistry, we use the Bohr planetary model to describe what goes on instead of the wave mechanical model because it's a little simpler. With that, if you have any questions, feel free to leave them in the comments below, and I will get back to you as quickly as possible. Thank you so much for watching. Have a good day.